Welcome to this afternoon class. Today we will continue on our topic, nuclear reaction, nuclear fission. We stopped this morning saying that the uranium can be split, release energy, etc. But before we continue furthermore and see the practical application of nuclear reaction, I wanted to start with this. But for this energy to be released, you need the appropriate material. We spoke about uranium-235, but there are others. Let's take the definition. You will need what we call fissionable material. Apologize for the pronunciation, you will see it written on the screen. Fissionable material and fissile material. Not sure if it's pronounced fissile or fissile, but you got the idea. What's the difference between the two? Well, this one is a subcategory of this. So fissile material are obviously fissionable material. Now, who belongs here and who belongs here? I'm gonna give you an example that is usually confusing, but hopefully this is gonna clarify it. Uranium, it has a family. When we say uranium-235, the most commonly used for civil nuclear reaction, there are others. Mainly, you'll have uranium-235, 92, and there is the other one, uranium-238, also 92. That means they have exactly the same number of protons. That is why they are considered isotope, because isotope are the atoms that have the same number of the protons, which is the atomic number, so the same atomic number. However, they differ in the number of neutrons. That is why here it's written 238 minus 92. It gives you the number of neutrons that this one has, and this one, as you could see, has 3 less neutrons. Why the uranium-235 is in the fissile material and his cousin 238 is not? Here's the answer. You remember this morning when we started the chain reaction, like the nuclear fission, we said that we will send the neutron on the uranium-235, it will split. And this one, I can also assure you that if you send the neutron on the 238, it will also split. The difference is the speed of that neutron. This one can be split by a slow neutron, because neutrons also have 2 categories. Let's put the different categories of neutron on the board. You have fast neutrons, and I will call them thermal neutrons that are slow. You'll see the energy that they carry. So there is this one and there is this one. The speed of the fast neutron, the energy they will carry, will be higher than 1 mega electrovolt. You have a mega, which is 10 power 6, that's like a million, right? The thermal neutron, which is the slow neutron, the one that we used this morning, the slow neutron that we sent on the uranium-235 and split it to release the nuclear energy, this thermal neutron will have an energy of about 0.04 electrovolt. So we are comparing 0.04 to 1 million electrovolts. If you want to see the difference, it's like if I tell you this is $0.04, which means it's 4 cents. We are comparing 4 cents to $1 million. Just you can see the difference in speed between the thermal and the fast neutrons. So if you want to split what we consider the fissile material, you gotta send them thermal neutron. If you want to split what we call the uranium-238, that is only in the fissionable material, he does not qualify for the private club of fissile material. This one, the uranium, will need a very fast neutron. The uranium-238, you split it with fast neutron, and the fissile material, uranium-235, with a thermal neutron. So this makes a first big difference between why we use the 235 to create the nuclear reaction and not the uranium-238, because the neutrons that they will need have a total difference, a huge difference in speed. Now the question you might be wondering, okay, what happens if I send a thermal neutron to the uranium-235 238? Well, simply, the uranium-238 will absorb that neutron and does nothing. It will just stay like that. It will not split. In fact, that's what the fast reactors, because you have different type of reactors. You have the PWR, pressurized water reactor. The country where I come from, France, majorly use that type of reactor. You have also the fast reactors that use fast neutron. The one we use in France use thermal neutron, slow neutron that have a speed way lower than the fast neutron. So not only the type of neutron that you need to send on uranium-238 and 35 is different, way different, massively different, but on top of that, when you split this one here, so this is uranium-235. So the uranium-235 will absorb the neutron, will transform into uranium-236, and that uranium-236 the uranium-236 cannot remain in that state. It's too unstable. It will split. It will split in krypton and barium. Right? Send neutron here. So this one transformed like this. This is like this. We said it's gonna release energy in form of heat, and that is why we are even bothering with all this story, the nuclear and stuff, is because we want to recover this heat released from the nuclear reaction and use it to boil water that will create steam. That steam turns the turbine generator and create electricity. This is very good because that's what we are looking for. Then we will have other neutrons created also. The story is not over. You have 2 new elements, totally new, and then 2 or 3 new neutrons. Of course, this is the major difference between nuclear reaction and chemical reaction. In chemical reaction, the elements in the beginning of the equation and the end are exactly the same. Here we just created new ones. The second difference between the uranium-238 and 235 is in the speed of these neutrons. So we said first, let's use green for this one, yellow for the 238. So the speed for the uranium, let's put it like this, uranium 238 and uranium 235, and let's compare both of them. Okay, the initial speed that you need for the neutron to split the 238 will be very fast. It's a fast neutron. It's gotta be higher than 1 mega electrovolt. This one will be around 0.04 electrovolt, comparing 4 cents to $1 million, just to give you an idea. Okay, the speed of the neutrons created by the fission of the uranium-238 will be under 1 MV. So this one, the speed of this one will be under the speed of the initial neutron that has caused the split of the uranium-238. What about this one? This is where it gets interesting. The speed of the generated neutron will be between 0.1 mega electrovolt and 10 mega electrovolt. So what is the consequence of this massive big difference? It's the following. Since the neutrons generated by the uranium-235 are faster than the original neutron that has started the fission, they will have enough speed to continue on their own way and start another fission, another reaction, another nuclear reaction. The other neutrons created by the uranium-238 will have a speed that is lower than the initial neutron. Therefore, they cannot start another reaction, another nuclear reaction. Even if they meet another uranium-238, that uranium-238 will just absorb them and does nothing. Why? Because what I told you, the uranium-238 belongs to the category of the fissionable material. He is not eligible for the club, the special club of fissile material. Why? Because the fissionable material needs fast neutrons. So these neutrons here, they will be absorbed by another uranium-238, but it will do nothing. It will just stay like that. It will not split. However, the uranium-235, the neutrons created by its fission, when they will meet another U-235, they will split. Why? Because they have a speed that is way faster than the original neutron. In fact, this is even a problem that is solved by something called the moderator in the nuclear reactor. When you look at the construction of a civil nuclear reactor, it has what we call the moderator. That is what we will see after. But before we see a practical application of the nuclear reaction, I think it's worth calculating this, the energy released by a nuclear fission. Again, why don't we simply burn coal? Why don't we simply burn gas and release energy? I get it, coal and gas have more CO2, that's a problem, but maybe we can find some technology to capture the CO2. Why are we going to this nuclear thing that has a lot of risks, like what we saw in Chernobyl and other events in the United States, in Fukushima, etc. So why are we bothering to go through all this stress? The answer is, let's calculate the energy released by nuclear reaction. So I will start with this. 1 gram of uranium 235 can release enough to supply 1 megawatt a day. So 1 gram, think of it, this is a gram, a ridiculously small amount of uranium 235 can produce enough energy equivalent to 1 megawatt a day. That means you can produce 1 megawatt during 24 hours. So let's start with it. 1 gram can produce 1 megawatt day. This is huge, because 1 megawatt, so an oven, like a little oven that you have in your house, consume 1000 watt, is like 1 kilowatt. This is 1 megawatt. It's like, imagine 1000 oven, you can supply with 1 gram of uranium, you can supply 1000 oven connected the entire day. Like, turn on the oven, let it for 24 hours, 1000 of them, and you need only 1 gram of uranium. You want to see the demonstration of this one? Here it is. We know that one fission, like of any fissionable material, one fission will release the equivalent energy of 200 MeV. So one fission release 200 mega electrovolt. So this is one fission. Mega electrovolt doesn't mean that much to me. I want to see something in joule, watt, etc. So this is equivalent to 200 10 power 6 multiplied by 1.0602 10 power minus 19, because 1 electrovolt is equivalent to 1.602 10 power minus 19 joule. It's ridiculously small, but we are getting to it. Now, to produce 1 watt, you need 3.1 10 power 10 fission per second. This is how many fission you need to do, how many uranium atom need to split per second, per each second, to produce 1 watt, because watt is joule per second, right? So you need 3.1 10 power 10 fission per second. This is like saying you need 31 billion fission per second to produce 1 watt, 1 joule per second. Until now, it seems very small, but here is the thing. In 1 gram of any fissionable material, how many nuclei do you have? Well, you have 2.5 10 power 21 nuclei. So if you take 1 gram, you will find in it 2.5 10 power 21. You see here we had minus 19, well here we have a 21 nuclei. So if you multiply all of this together, it will give you 1 megawatt a day. In fact, if you multiply all of this, let's do it. So you have 200 multiplied by 200 mega electrovolt multiplied by 1.602 10 minus 19 multiplied by this 3.1 10 power 10, then multiplied by 2.5 10 power 21. Divide all of this by the number of seconds you have in a day. So 60 seconds multiplied by 60 minutes multiplied by 24 hours. If you do this calculation, you will find a little bit less and then 1 megawatt. And because I divided by the number of seconds per day, so I know it's 1 megawatt day.